So let's talk about sonics. How does a sonic anemometer measure wind? An acoustic signal is a pressure wave being propagated by the air medium. So think of a speaker, and it pushes on the air, and the air molecules push on other air molecules, push on other air molecules, push on other air molecules, and that acoustic energy propagates through the medium. All right? That's inherently different than, say, electromagnetic radiation that isn't interacting with the medium itself. And so because it's the medium that's carrying that pressure pulse, then the time that it takes to get from, say, a transmitter to a receiver will depend on whether the medium is moving, just like an airplane in a tailwind, or an airplane in a headwind. So air or wind along this acoustic path in this direction, the same direction as the way the acoustic signal is being propagated, will get there more quickly with the tailwind, and in the next slide you'll see it gets there more slowly with the headwind. All right? So we can use that, and I mean, you learn this in elementary school, that distance equals rate times time. That's the only thing you need to know to do sonic anemometry, is distance equals rate times time, or the time of flight from here to here is the distance between the two transducers divided by the rate of travel. But the rate of travel is affected by two different things. All right? One is it's the speed of sound in still air, and it's also the component of the wind along that path. All right? So I've represented wind in general here, and it can be broken down into a parallel component and a perpendicular component. The perpendicular component does nothing to that transit time. The parallel component either aids or inhibits the propagation speed. All right, so by making this one experiment, transmitting from here to here and measuring that time, we can almost figure out what the wind is and almost figure out what the speed of sound is. The problem is that we have two variables and one equation, two unknowns and one equation, right? Because we don't know the speed of sound and we don't know the parallel component of that path. But if we turn around and transmit the signal in the opposite direction in a relatively short time frame before the wind and speed of sound change, which would be on the order of millisecond,